I welcome you all again to the second session of day 3. And we are privileged again to have Professor Maurya among us. And as you can see on this slide, he is going to talk about zeolite-Y encapsulated heterogeneous metal complexes as sustainable systems for catalytic oxidations, a challenge for chemists and chemical engineers. So, again, we are going to have a learning experience for another 1 hour. So, sir, welcome. Welcome again, and it's over to you. Thank you.
Thank you, madam. देखिए, अगर ये लेक्चर अच्छा नहीं होगा तो हमारा कोई कसूर नहीं है। हाँ, मैं बता देता हूँ पहले। ओके, ऑल राइट। हाँ, okay. Now his topic is very close to the previous topic, but is slightly different, and you may find some slides even common because ultimately it's catalytic reactions, right? And of course, again, that will be almost similar kind of metals and oxidation reactions, right? So now the topic here, that zeolite-Y encapsulated metal complexes basically, and of course that will be heterogeneous in nature. Now, second, a challenge for chemist and chemical engineer is in question mark. Okay, the question mark is missing because he did not put the question mark. Okay, in the title, a question mark. There is really, is this topic is really challenging to chemists and chemical engineers or not? We will try to answer it. Okay, so to start with, again almost similar slide, catalysis. Okay, see the role of catalysis. When you look at there, almost more than 90% of petroleum refinery petrochemical process are catalyst based, and 90% of processes and 60% of products of the chemical industry are actually catalyst based when you look at that among heterogeneous. And 95% pollution control technologies and alternate fuel productions are governed by the heterogeneous catalyst. Means heterogeneous catalyst is dominating over homogeneous catalyst. The reason I mentioned the morning itself, the reason is because the recovery of the catalyst or the separation or the difficulty in separation of the catalyst from the reaction mixture. Okay, because of that, people started moving towards the heterogeneous side. There may not be that heterogeneous catalyst that good what homogeneous catalyst does, or that shows the catalytic activity, but even if a 10% catalytic activity is less, and if catalyst is recyclable, it can go to certain extent, certain cycles, then it's always better because you are ultimately not losing anything, you are gaining, though you are getting the less conversion or less oxidation, less active. That is fine. Okay, so see the there, this is given here in detail, that industrial catalyst heterogeneous these days approximately covering 80%, and homogeneous is about 17%. So you can see the ratio. Earlier, during the type of during the time of Ziegler and Natta, homogeneous catalysts were more popular because those days heterogeneous catalysts were not much known. In other words, I would say that. Okay, and now biocatalysis is coming up, and in the future, in near future, you will see that this figure, what is 3% here, it may dominate because this is very safe. Green kind of catalyst, you can now name it, because these days people are talking about green everywhere. As soon you write something, even you title up your paper green, that people see through attention. Okay, because immediately some feeling comes in the mind, why green is written, let's look at that. Okay, so the green chemistry became an entirely different field because of this one. And also people are talking about too much pollutions, too much poisoning, to the human being environments is coming up. So the heterogeneous catalysis and biocatalysis have a future. But whether the topic what I have chosen is really having future or not, we will look at that. The demand for catalysis, see, these days almost 4 to 5% is growing every year. It is growing up. Global catalysis market size, it is given here in 1993, 1991 data. Sorry, 2019 data. All right, this is like 33.3 billion in 1990. See, 2019. Huge market is there. Okay, so and it is expected that in the Pacific area, Asia side, this is going to be more and more and more in near future. Okay, so catalyst contribution in the nation building, how it is contributing. Always look at the GDP is covering 24% of that. It means they are having some future because of the heterogeneous nature that is important in general. Okay, we look at the all. I mentioned the previous slide. Only what were you looked at? Fertilizers, pharmaceuticals, or in talk in terms of fuel, energy, everything that is covering these days. Okay, so it means the heterogeneous catalyst has a future and it can dominate. It is dominating over the homogeneous catalyst because they are recycling in nature. They can do further. So in the morning I talked about one of the process for say how to make a heterogeneous catalyst. Even if we have a homogeneous catalyst, if you can polymerize it, you can make it heterogeneous. What you need to do it, you make it insoluble in most of the solvent. Okay, and then it can be used. So in that terms, coordination chemistry plays a very important role. Select the ligand in such a way that it can make a polymeric material, polymeric compounds, polymeric metal complex, not mononuclear. Go for polynuclear, not even dinuclear, trinuclear, that may have some solubility issue. Okay, solubility means they may be soluble, but when you polymerize it, that can go very easily and you can make it heterogeneous in nature. That works on the basis, on the principle of the homogeneous itself, but because that is insoluble, reactivity, activity may be a bit slow, but it works. And we have tried it in the beginning when I started my career by polymerization of the metal complex. It worked, and catalytic tea is not bad. We can do that. Another process, that is immobilization. What I presented in the morning, I used organic polymer. These days, inorganic polymers are also very well known where the materials can be immobilized on the surface itself. You may be knowing some of them like MCM 41, SB. These are all like silicates, aluminum silicates, substituted aluminum silicates, and others. And they are porous materials working very well. They are polymeric materials. There can be homogeneous catalyst can be embedded through covalent bonding, through adsorption, but they are working very well. So that is one method. And the last method, what I mentioned here, that is almost similar to the number 3, but this is zeolite encapsulated. Okay, so let's talk about some zeolite first and then encapsulated one. Okay, zeolite. Most of you must have read now because this now you can find this one even the course of like 12th standard also. The definition is given there at least. What is a zeolite? It's a simple aluminum silicates in general when you talk about, but having some framework. And we look at their three-dimensional network of interconnected large spherical cavities known as super cages. They are called super cages. Okay. And when I look at the structure, may not be very clear here. I'll show you another slide. Okay. There you will see a good large cavity. Okay. So there the linked by opening defined by 12 oxygen rings. Okay. Structure provides a high surface area, specific pore size, making it valuable application like catalyst itself. So zeolite itself can act as a catalyst because aluminum is there, silicate is there, and it depends on what kind of zeolite we select. There may be some metal ions attached along with that. So that itself can act as a good catalyst, a heterogeneous catalyst. When make it metal complex encapsulated, then definitely that going to make a difference. Okay. So when you talk about that, see, hydrated aluminum silicates because it has a big void, lot of solvent like water molecules can be there, and that actually helps in finding out the pore size itself. You need evacuate or remove it and measure the pore size. That can give you very idea. Okay, definitely. And also this is three-dimensional network, contains channel or interconnected voids. The formula that is more important. See, M2 by N O ALO2 X SiO2 YS2O. YS2 Y may be more than 100 because it depends on the size of that cavity. Okay, and number of negative charge equal to wherever negative charge comes, mostly balanced by the aluminum. Whatever remaining, that is balanced by either hydrogen or any metal ions. Okay, that is the beauty here. X is generally are equal to greater than 2. Number of water molecules is mentioned, it gives the volume of the channel. Zeolites are both crystalline and porous type. I'll show you some structures. Maybe that what is called that FESM. Okay, and beauty that when I mention here M2 by NO, okay, M can also be hydrogen, H plus ion can be simple hydrogen, and it can be any metal ion. And good part of this zeolite is that hydrogen ion can be replaced by metal ion and vice versa. Metal ion can also be replaced by hydrogen. When you take in the acid, proton takes up. When you take into the base, the metal ion takes up. Like sodium hydroxide, what I'm talking about. Sodium chloride, simply if you have a H zeolite, treat in the water with sodium chloride. It's a saturated solution. All it's not all, but most of the hydrogen can be replaced by the Na plus because the rest, whatever balance charge coming up, that is taken up by the sodium ion. And also sodium ion can be replaced with the metal ions, other metal ions, transistor metals, what we talk about, because that can enter easily into the what is called the cavity. Okay, so this exchangeable property of this hydrogen versus nitrogen, or sorry, sodium, or sodium versus other metal ions, that is a very good, you will find later. Okay, so this is good. Other thing is that homogeneous catalyst, mostly metal complexes. I mean, organic chemist talking about metal complexes may be considered as one of such interesting molecule which can be inserted into the cavity. Okay, and zeolite encapsulated complexes then can act as a catalyst. And benefit of this one is because you have a homogeneous catalyst after insulating into the zeolite pore void, you are making it heterogeneous in nature. So beauty there is that if you have a little bit smaller size, then the cavity you can move around. It is attached to van der Waals forces, or the metal and attached connected to the aluminum, or somewhere connected it because you have exchange hydrogen ion for the M plus ion, and it can move around within the cavity of the zeolite. So there, enjoying both properties, homogeneous catalyst because it's metal ion, metal complex, and heterogeneous complex catalyst because it cannot come out of the cavity. So if I talk or if I compare, in other words, around which say polymer supported catalyst, what I talk in the morning, and now in the afternoon, this material may be better than your other polymeric are materials supported on the polymer, because there it cannot, if it cannot come out of the cavity, there is no question of leaching from there unless that compound is decomposed. So under the condition when compound doesn't decompose, if catalytic activities are carried out, this should give you better catalytic activity, better performance than the material supported on the polymer. Okay, so that is the question. Okay, with this question we move on. This is the one. Now here picture is very clear. If you look at there, there are one, two, three, four. Can you see the four holes where material can enter into? All sides it can enter. You have a small pores on the outside and then big one inside. Like we have a ball, cut it from four different places, make a small hole, let the material enter it. Suppose you have a squeezable ball, okay, and it enters and then expanded. It cannot come out with any other way. unless you break it down. That is the beauty of this zeolite. Okay, and when you look at their side, some T is equal to silicon and aluminum, then you have oxygen and sodium. You will find that different places sodium ion is there. Why sodium ion? Because those hydrogen ion are replaced by the sodium ion. Sodium ion, sodium is called NaY zeolite. Sodium zeolite. Why? Why? There are different categories. Their name given depends on the cavity size. Okay, and the beauty here is that even aluminum can be replaced by other metal ions. Okay, under certain condition, or when you are making this, because this can be made in the lab. The very National Chemical Laboratory, they used to prepare in kilogram quantity, because there a long time project was there during 1990s working on zeolites. If you know the IPCL, Baroda, there lots of projects were given from there to NCL, and NCL returned it some good, you know, what is called catalyst, and and they used to use that like patented catalyst. Okay, so here all sodium ions can be replaced very easily with the other metal ions. As I mentioned in the beginning, that if you have a simple hydrogen ion, you treat with like mild sodium hydroxide, so all hydrogen can be replaced, or most of them can be replaced. And then if you have a little bit concentrated solution of any metal ion, simple distilled water, you dump your zeolite, you add metal salt, stir it maybe for 24 hours, you will find that most of the sodium ions are replaced by the metal ion. Okay, so there now you have a metal, like transition metal, if it transition metal exchanged Zeolite-Y, now metal ion is available. So if ligand, organic ligand of course, can enter into the cavity, it can react easily with the metal ion, and then it can form a metal complex. So need is to make a device how the ligand can enter into the cavity, it can interact with the metal ion to form a metal complex, and if size is compatible, it cannot come out of the zeolite, because inside cavity is bigger, sometimes as high as 12 to 13 angstrom, and the small that is having 4 to 5 angstrom only. It cannot come out of that. Okay, so how to make the metal complex? So there is one method called flexible ligand method. I'll discuss all one by one, maybe if possible. Template synthesis method, zeolite synthesis method, ion exchange method, absorption method. Okay, and as I mentioned here, that during 1990s, this was the project when the then deputy director Paul Ratnaswamy. I was also there in NCL for some time. Okay, working as a pool officer. Then he called me one day, Moria, I have got one review article, very small review article was there. Just you read it. You are an organic chemist, and I think you can find something interesting in there. I read it. Then I discussed with him. Sir, this is like this is talking about. They are talking about metal complexes encapsulated in zeolite. And you know what was name was given? Sip in a bottle. Sip in a bottle. How, like you must have seen in the market when you are going to somewhere, really bottle and sip inside there. You will find it like market where you are going some picnic spot or other place. You will find that. How this sip is made inside the bottle, that was the question. The same thing here. That name says that sip in a bottle complex. Now, question or name letter came that metal complex encapsulated zeolite. That's all. Okay. So then I thought, how to do that? Is it possible? Then I read through. Then we actually able to understand that this is the way to move on. You first you have a NAY, then exchange it. You can have a material, whether you have metal exchange material, and this is the one. This slide is shown here, like you have a CO2 plus ion. So not 100%, but 60, 70, some percentage metal ion can be inserted into the cavity, okay, of the zeolite, and then you have a solvent. Earlier, what we started that we are not able to understand very well. So we selected such a kind of ligand which are having a good melting point. Okay, melting point means a certain temperature, it will melt and form a liquid. So have a excess amount of ligand, melt it, and you add your zeolite where you have a metal exchange zeolites available. So that used to enter into the cavity because ligand is flexible in nature, enter into the cavity, react slowly, then separate it and then wash lot of solvent by stirring into the excess of solvent and then remove all excess ligand. Okay, then later we realize that we can go by regular solvent, just take this material in any solvent and where ligand is soluble. So when ligand is soluble, it have a flexibility in nature, it can enter into the cavity very well and it can form a metal complex. So this was the idea that was generated during 90s. Okay, and then when you have this material, solvent enter into the system and form metal complex, you can also visually see that when you filter it, if suppose you have a copper complex and it forms like suppose you have a nickel complex, you know nickel DMG complex, very pinkish in color, zeolite is white in color. So as soon metal complex forms, the color of the zeolite change. So you will have a pinkish color compound, you have bluish color compound, though the metal content along with the metal complexity or the total amount of metal complex is very less. But the shade you can immediately see that change. You will find that it has entered into even after lot of extraction with the other solvent where ligand can be all washed out. This can be seen. Once the metal encapsulated complex is formed inside the cavity, there is a good possibility that all metal ions do not react with the ligand. Then, if metal ion itself is present, you know that metal ion can act as a catalyst itself. So, we need to remove those metal ions. So, what do you do that? Then reverse process. Treat with this sodium chloride solution for longer period. So, slowly all metal ions can be exchanged with Na. So, Na metal complex zeolite where sodium ion has to be there definitely all the time. Okay, so then you have a say the simple ligand was there when I talking about the melting point, melting of the ligand. So saline was the best because this could melt around 120 temperature very easily. So you can increase the temperature by say 140 and then it becomes a liquid state, it can enter into the cavity. Okay, so that was, but later the process was modified and the Paul Ratna Swami and his group, because I left after 2 years. So he that initiation was by me, then his group to his research scholars, they extended this one and they prepared lot of compounds and then published paper and got the PhD thesis. Okay, so that was the initiative. So here now other method is there. That was the flexible ligand, but now the other method is that is called that absorption method. Adsorption method. It's not. It should be adsorption. Okay. So here first step is same. Now in second step, see, this is through when you have metal exchange solid materials, then pass different gases like you know that carbonyl. In the morning you were talk your topic was in IR different carbon monoxide adsorption. Adsorption. Okay. So there when you pass through like mixture of carbon monoxide and hydrogen or sometimes carbon monoxide and water, like when you pass through, so if metal exchange zeolite is there, then carbonyl react with the metal ion and form metal carbonyls. Okay, this was that is called that adsorption method. Okay, so you have like different kinds of compound made there, like NiCO4, IR4, CO2, etc. All carbonyl compounds, because those carbonyl compound, if you go to the catalytic chemistry, you will find a lot of application of carbonyl compounds in different reactions. Okay, so these were the method evolved for the metal carbonyl preparations in encapsulating zeolite. And then the template method is there where you have a ligand separately, you have a metal ion exchange zeolite. Like if you look at the bottom structure is a macrocycle. Macrocycle cannot enter directly into the cavity because this is not flexible. Silent ligand, other ligands are flexible enter, they can enter into. So how to do that? then you have to go for template method, where like the first step, we have a diamine compound, orthophylline diamine, taken to the solvent, that will react with, because that still is a, like bidentate ligand, it can react with metal ion. Then if you add like diketone, it can enter also, because it's a liquid phase, it can enter into and react with the NH group, NH2 group there, and can form a bond, double bond, like azomethane group, and can form macrocyclic inside. So you are tailoring the formation of macrocyclic inside the cavity through the template method, and you can prepare it. Now, this is again example of the template method, where see, this is designed, you have almost like a saline type ligand. You know saline means, I'll show you structure. Ethylene diamine and salicylic interaction, that becomes a ligand which is having two azomethane group, salicylic group this side and ethylene diamine connected through azo group. Okay, so this can be prepared, and when you have a, that is called the zeolite synthesis method, then there, like phthalocyanine porphyrin molecules are encapsulated with the zeolite. What they have done is, they have a starting precursor, silica, alumina, and sodalite, and then fused together along with the precursor of the porphyrin or phthalocyanine. There it mixed and heated at high temperature, so that they, and in the solvent are others, so that the zeolite formation occurs at the same time the phthalocyanine formation both together, because you have all fragmented. Okay, so when it comes all together, it will form their phthalocyanine and metal complex inside the cavity only. Okay, and then you wash out, remove everything, and then you have a encapsulated metal complex. We have applied the flexible ligand method to prepare such metal complexes. Okay, and here when you look at there, the strategy is same. There is no change for that. Strategy is same. So we have prepared that in first step, that compound. Now the Y represents the zeolite. Basically here we cannot make it all that way. And then by sodium chloride exchange, all excess metal ion has gone out and OH group is replaced by the chloride ion. So this metal complex has formed there. Okay, and the same one, like when you have a vanadium compound, like vanadium precursor, vanadium salt, treat with, you have a VOI in cap, that like vanadium oxide exchange zeolite, and then you have a ligand. In the case methanol, reflux it for say 24 hours in the presence of oxygen. You will ask the question, why oxygen is there? Now, sir, your question, vanadium 4 and vanadium 5. Okay, paramagnetic diamagnetic, because characterization of diamagnetic becomes a little easier, so we have used air. So vanadium 4 oxidized to vanadium 5, and the ligand attaches there, so that will form double bond, V double bond O, V double bond O, two oxo groups are attached there, and it can be seen like this way, vanadium complex encapsulated with the zeolite. Characterization becomes a little easy, because then two cis bands can be seen very easily. Okay, in the IR. Now, how to characterize? That's the question. Characterization, when you have ICP-MS, you can find the metal content. Okay, through FESEM, you can find morphology, and also you can find the metal content. Through TGA, you cannot find metal content here. The reason is because you have alumina, you have a silica. Silica is highly stable when heated. This will not further decompose, right? So metal content determination through TGA it's not possible here. The only possible way is through ICP-MS, and one more. What is that? Metal content, other method for the metal content estimation. Okay, so we can see that once metal content is there, still we cannot say that this is encapsulated. Then you have to determine the nitrogen. Nitrogen, like any method, it can be used. So when we have a metal nitrogen, because most of the ligands are having the metal nitrogen content and metal content. So once you have a metal and nitrogen content available, you can approximate the formula of the compound. Okay, TJ, see TJ is giving 7% or 4% like loss up to 100, up to 800 is how much loss is there between 250 and 800, 10%. Because neither alumina nor zeolite is going to decompose it. So, but that gives you feeling that part of the in the beginning when you heat it say 150 to 250 degree, say between 150 to 250, below 125 there may be some like moisture other content can come out from the cavity of the zeolite. Still lot of water molecules are trapped inside, they cannot come out so unless you heat it at higher temperature. So because of that in the beginning what is and water molecule is coming out, after that definitely after 250 only that will come due to decomposition of the metal complex. All right, so that can give you idea about the decomposition of ligand, and whatever the percent content you are getting that is coming due to ligand present in the cavity. If that is perfectly washed and all non-reacted ligands or free ligands are removed from the mixture. Oops. Now see characterization, scanning electron micro, whenever you do this, when you have a only metal ion exchange, you will find the surface not crystalline in nature because part of the metal ions are present there. Okay, maybe on the surface, inside the surface you will find not very good one. But once the metal complex has formed and it is washed very nicely thoroughly to remove any metal content or metal and metal complex from the surface, you will see that the sharpness in the crystalline nature of that zeolite, that gives feeling that the crystallinity of the zeolite is still maintained after encapsulation of the metal complex. Only that much information your morphology can give. If you have a ACM attached, EDS attached, that can also give some idea, but that does not give correct idea. The reason is because in the zeolite encapsulated metal complex, your metal content is inside of the cavity. Okay, if it happens that when a pore is void is available, hole is available, through that if instant light goes there, can give you some idea. So some metal content definitely you will see, but not the 100%. Okay, so that is the only problem, but still you can see that you can have idea. Other thing is that electronic spectroscopy that is helpful to sometimes, but again how to record the electronic spectra, the one what I told in the morning, that grind it in the nozzle nicely, make it very like suspension like emulsion type, make attach what is called the paste in the cuvette in one, and other one make it nozzle reference, you should be able to record it, and sometimes we get good information out of that. So if you have a say charge transfer band, you should be able to see that. If you have a like band due to organic moieties transition like pi n to pi and pi to pi transition, you should be able to see that. And sometimes if you have a unpaired electrons, then DD bands you can also see that. It's possible, very good possible. Okay, so that can be characterized. So all the see IR is listed here and UV visible listed. You should be able to see that. And then characterization by powder XRD. People have used powder XRD very frequently to characterize it, but frankly speaking, this does not give any information related to metal encapsulated complex. What is information that XRD gives about the crystallinity of the zeolite? Whether you have a NAY is perfectly crystalline, all peaks are coming due to, because you know that crystallinity means peaks are sharper, right? So from first to second to third, what you get it that even after exchange of the metal ion, crystallinity is maintained. After encapsulation of metal complex, your in crystallinity is maintained. You will see that there is no change in peaks. 1, 2, 3. I do not see any. Now, the question comes: what about the metal complex? Do you get any peak due to metal ion? Very rarely, small is called tiny peaks sometimes. If you have a considerably good amount of metal complex encapsulated in certain number of void or the whole, then you should be able to see, otherwise you won't be able to see that. But at least gives idea that crystallinity is maintained even after exchange with the metal ion and exchange with the metal ion interacted with the ligand. Okay. Anyway, that is good enough to see that. Now, these are some characterization. We were see when we started chemistry at IIT Roorkee, there was no facility except FPSM and powder. That's all. Nowadays, facilities are available. I wish I could do some chemistry, but I haven't done that. So when we started, after doing all characterization, we tried it. Let's try simple catalytic reaction, very simplest one. This was before I started the polymeric materials. Okay, so this one is simply very see phenol. Phenol is there, oxidation of phenol, which the phenol, polyphenol, etc. That can be oxidized very easily. That can give you a good materials itself. So, see phenol being ortho and paramagnetic, sorry, ortho and para directing group, the product form will be see ortho position and para position, right? So with this one we started it, and we tried to do the, because there was no GC available when we had to rush to the chemical engineering, and chemical engineering has one GC where you have to note down the reading all the time. Yes, manually when you're running it, run and then note down the reading. Those days in 2002, 2003, etc. Okay, but at least we are able to see that some converging is going on. How much it was difficult, very difficult, maybe plus minus 5%, but gave some these catalysts we use. This is the like silent type of ligand, the second one copper compound. Okay, that you see that it should be ethylene diamine, it is propylene diamine. That is the one. Okay, so how to see that? That was first thing is to see the optimization condition for that, because we are using oxidant. So how much oxidant is required to get the best result, how much of catalyst is required to give the best result. Okay, so and if we are doing the reaction in solvent, how much temperature is required. So all optimization has been done one by one, and then after optimized condition we have say this four different, this is related to S2O2 concentration. You will see that some best result coming at certain condition. Then we have amount of catalyst, effect of temperature. So when you look at all and combine all these things to the optimized reaction condition, then this is the one for the phenol oxidation for the 50 millimole. 50 millimole is too much amount, but we started with that. And S2O2 you require almost like 1:3 ratio, catalyst 25 milligram, temperature 80 degree. Minimum solvent is required to do this reaction. And look at there here. When you have a zeolite encapsulated, when we have a simple metal complex, when you compare it, zeolite encapsulated is giving best result. Though little bit more time is required, but it's okay. But catalytic activity is really better. But when you talk about in terms of the real good, the result is really good. It's not, because conversion is going maximum to 40 to 45% in any case. But it's better. But some results are coming. So those days we started with, and then this is the data, based on the selectivity. Of course, again, that we used to note down the what is called that area under peak. We used to note it down by hand, everything. Okay, so that data anyway is giving a good result. At least we are able to do that. So 40% conversion of the phenol is there, and with all cut collar hydroquinone formation. Okay, then we study the another reaction, which is the styrene. Styrene gave us 5 different products. What we expected that styrene should give styrene oxide, epoxide best, not other products, but definitely we are not able to optimize to get maximum product like styrene oxide. Not, it was not possible. The reason is because oxidant ultimately oxidizing styrene epoxide to the other product. Okay, but it worked, and we were able to find out all different 5 products. By that time, during 2007, we got one GC in the instrumentation center. So we are a little bit better in position of that one, and we are able to do that. So this is for the another one. See another catalyst. So optimization, now you are familiar with how to do that. Okay. And for the styrene oxide, styrene, this is the optimization condition. And in that case, you will find that S2O2 we are using 1 is to 3. The conversion is very good. It is going almost like 93, 94%. But again, since we have a 3 times hydrogen peroxide, this is further oxidizing styrene to the other products. Okay, but conversion is very good. When you compare it, then you will see that the zeolite one is working really good, and within copper and vanadium, vanadium is giving good result. Okay, so vanadium acting as a better catalyst. However, when you compare within zeolite and non-zeolite, then there you find a big difference in their catalytic potentials. This is the data. You see that as high as 97%, copper is giving only 56, 57%. And when you see the styrene oxide, not, I mean, very pleasant result for the styrene oxide. The reason is because it's converting into another product. What is maximum is coming like uh, phenyl diphenyl ethanol, or even going to benzoic acid. Benzaldehyde is maximum, so that is expected. Okay, so why it is going to the benzaldehyde board? This is one of the reason we gave during that period, that is styrene is going to epoxide. But since you have excess of hydrogen peroxide, it is further reacting with opening that ring that is known to open the ring, and then breaking it down, giving the benzaldehyde and the maximum yield. Now, the reaction what I talked in the morning. So we wanted to see whether this is working with this condition also. So we have taken sulfide, and we are able to convert it at even room temperature. See, optimized condition already given here. Okay, and then for the 5 millimole of the substrate, S2O2 require only 5 millimole, catalyst very less amount. Room temperature in acetonitrile, this is giving very good result. Okay, conversion more than 90%, very good result, and giving sulfoxide in very good yield, which is expected one. But if desired one is should get only sulfoxide, but some cases giving some percentage of sulfone. When you do without any catalyst in the presence of oxidant, then you will see that the result is very different. It means our catalysts are becoming more selective towards the sulfoxide, not the sulfone. So we are getting good amount of at least sulfoxide. Now, to propose the mechanism, this is one of the important part, that you take the help of the homogeneous catalyst. Okay, and when you titrate this regarding the UV visible spectra of the compound at different concentration of H2O2. Okay, so what do you see that when you add drop wise the solution of methanolic solution of H2O2 to the solution of metal complex, see the spectral changes, and during spectral changes you find at least 2 to 3 isosbestic point, and that suggests that the vanadium compound VO2 is converting into peroxide species. We could also record the EPR, not EPR, record the 15 vanadium NMR, but here the material is not much suitable for 15 vanadium NMR. So, restricted with only this UV visible spectroscopy, but the isostatic point is very helpful in concluding that the dioxo species is converting into oxoperoxo species, and then oxoperoxo definitely the oxide of the oxygen of the oxoperoxo is transferring oxygen to the sulfide, converting into sulfoxide and sulfone. So that way, similarly in copper complex, not very encouraging result, but still you could see there the spectral changes here, but no isosbestic point in this case, because copper peroxo formation is not straightforward. Okay, there peroxo is mostly known there. They have a formation of peroxo through dinuclear compound. Okay, like two species coming together and forming, so you will not get very good or encouraging result that good, but still some spectral changes can be seen there. So particularly for the vanadium, this is proposed one, and that we also showed this slide to the previous lecture, but this is the best way to go it, because here peroxo formation is clearly seen, and so the reaction mechanism can be proposed. Now the question is recyclability. This compound or these catalysts are very good recyclable. Okay, the reason is because, and that recyclable under the reaction condition, that is important. When you heat excess, definitely that compound has to decompose. So under reaction condition means when you have 80 degree, 100 degree temperature for the catalytic reactions, during in the solvent, compound is not decomposing at all, because this is entrapped into the cavity. It is just moving in the cavity. It can move it can change the position, but it cannot come out of that. When it cannot come out of that, cycle recyclability becomes very easy. And also to check it whether this is heterogeneous, the reaction is heterogeneous or homogeneous in nature. May some ask question may come that maybe the catalyst homogeneous coming out of the cavity into the solution and acting as a catalyst, means part of the leaching occurs. That's the question. So to answer it, we have tried to solve it, that you take the zeolite encapsulated complex into the solvent where you are doing the reaction, and after reaction, okay, you just remove the product, add more solvent there, and right there, sorry, filter it, we have, keep the catalyst out. Now if leaching has occurred, if you add a substrate and oxidant, more reactions should, I mean, more reactions should occur, but there is no further reaction after adding extra solvent, sorry, extra substrate and oxidant. The reaction is not moving. The percentage of the conversion remain the same, means there is no leaching of metal complex during the catalytic activity. So that is a good part, means the catalyst is recyclable. Other way, we have also done that. Separate the product from the reaction mixture, wash the zeolite insulated complex with acetonitrile, dry at 120 degree, and do the further reaction. Taking the same amount is giving the same, almost same product, same conversion. It means catalyst is very stable and not reacting it. Okay. So we have moved further. So now we have prepared, see, these different kinds of cell and type of ligand, with now the orthopylene diamine replaced by the cyclohexylamine. Reaction is same way. So characterization, you will see the metal percent we have done it, and the surface area, because it's not done by IIT Roorkee, somewhere else it was carried out. Okay, some data were obtained, so just mentioned here, and then see the TGA here. You will see that going from 110 like 100% OT up to 80%, not going beyond that. It's so stable, means partly decomposition has occurred in 2-3 different places. See, in the beginning, some water molecule, then up to 350, all water molecules what were trapped, and then at the end when it's coming between 350 to 300, 600, that is only due to the decomposition of the metal complex. So that could give idea. Okay, so 3 different decomposition temperatures are seen there. Now, same story for this one, you will find almost similar. Even if you take one and put it again in the separate another paper, no one would be able to see that. Only the expert can see that the same data, same what is called that is given or not. So better to record it. Don't, you should not cheat it. Okay. So that way it is done. Then UV will use spectroscopy, that gives very good information. Okay. We are able to see the band due to, because this is shown by copper compound, this is shown by vanadium compound, so the charge transfer transition can be seen very nicely. Only thing is you have to record in the suspension or the mole, paste it and view it. You can record it. So that's a good part. We could see that. Then catalytic activity are done here again, and the conditions are fixed in the particular reaction, and then here result is better, but the conversion, when you look at their distribution of products, are almost same, not much difference. Okay, but again, when you compare with the other, copper and vanadium encapsulated is always giving better result. Now the question comes, that's why I love vanadium. It's not definitely not due to this chemistry, okay, but it's giving good result. So at least we are happy that this is chemistry is good. Then the regular cyclooctane, cyclohexane, this is the best way to check it whether your catalyst is active for the oxidation reactions. Okay, whenever people do that, people start with either cyclooctane or cyclohexane to see if your catalyst is active for the oxidation. This is the best way, like a model reaction to carry it out. We have also carried out it, but again the reaction condition has to be optimized. Okay, and under optimized condition you are giving four different products. Epoxide, you have a cyclohexanol, cyclohexanone, and then you have a 1,2-diol. Product distribution, this is under optimized condition. You see that vanadium on the top, encapsulated one, and the different products. Conversion is very good. Catalysts are working very good, recyclable, and only problem is with the, we are always worried about the epoxide. Okay, we did not know how to control it in the beginning. That is fact. Imandari said. But later we have done it, but we observed that if the reaction is carried out under basic condition, because acidity of the zeolite is the major factor to control such a reaction in terms of the product. When you make it slightly basic, you can control the formation of epoxide and you can increase the conversion of epoxide. Sometimes when you change the ligand, that also works. I'll show you that. Now we have a cyclohexane. You can do that oxidation easily. Conversion is a bit less, but under optimized condition, you will see that this is going to give you the product. Low conversion is not that good, like we have taken with this vanadium compound or the copper compound. With cyclohexane oxidation not an easy job. Okay. Now, see some more compounds we have tried one by one and tried to do the all catalytic cyclohexane oxidation, epoxidation, sulfide oxidation, etc. So I won't spend time much here, and then we move to certain others. See similar product, not much, no much change. Okay, but here you will find something different. When we have this ligand, that is called, when you have taken orthohydroxybenzene condensed benzaldehyde and making catalyst vanadium and copper, when doing this epoxidation here with the styrene, and here we have taken TBHP, tertiary butyl hydroperoxide. See the difference. Here we have 6.8 to 15% highest and sometimes even a 0 for the styrene epoxide. But in case of this one, when you take TBHP, possibly this is mild oxidizing agent than the H2O2. And when you have a styrene epoxide form, it is not going too much to the other product. So the here you can see that the epoxide is in much better yield. Okay, but as I mentioned that if you do the basic reaction, it is not done in this case. In other case, we have done the polymeric supported materials. It works better and give you better result. Okay, so in content we have prepared some other ligands. And see there some vanadium compounds, some either copper compounds are shown. Vanadium compounds have also been prepared, and then after characterization these compounds, here we have tried to do EDX now available. Okay, and EDX you will see that one copper peak can be seen there, a small peak is there, so that gives the idea. But as I mentioned that you cannot see too much. Sometimes when you are lucky you will see the small peak, but not like, because it's inside encapsulated, so you cannot see really well, but that gives some idea. But EPR spectroscopy is very helpful, not the krypton vanadium like other case I talked about. EPR is very helpful. After comparison with the homogeneous catalyst with the heterogeneous catalyst, you can get idea. You may not get those sharp peaks, but the major peak can be obtained, and you can calculate if you are lucky to get it first, and then calculation, if you know, you can calculate it. So all parameters are almost same like in homogeneous. Also, you can find in the heterogeneous catalyst with slightly difference. UV visual spectroscopy is very helpful in characterizing that. The charge transfer band can be seen in case of the metal complex as well as in zeolite encapsulated. Now here all reactions are done again with this system, and we'll see that now epoxide, even after changing the regular ligand to that one, epoxide is not very encouraging. We are getting mostly the benzaldehyde. And the reason is that because epoxide in the presence of H2O2 is breaking down the epoxy bond and converting into the benzaldehyde and of course the benzoic acid, etc. Okay, with manganese, just to see it if the metal change helping. So we have done some reaction with the benzoin, and the major product is actually dimethyl acetyl. After breaking the bond between the benzyl is 30%, benzoic acid 10%, and dimethyl acetyl is the 10%, almost 60%. But conversion is good. That is, at least we can say that. So this can be done, and benzyl is not the bad product and not bad in yield, and this is useful in other organic reactions. All characterizations are shown here, and here you will see very clearly that even in encapsulated recording these electronic spectrum in usual, all DD bands even can be seen, though it is not much expected for the manganese compound because this is what is called that it's been forbidden. But due to change in symmetry or broken in the symmetry, if you know the basic, you should be able to see the DD band, and of course charge transfer band can be seen. So it is seen here. So it means the symmetry has broken down and you are getting some results. Okay. And also in case of vanadium, it is very clear to see that. Okay. Now, as I mentioned that H2O2 titration, you will see that H2O2 titration very clearly seen that one isosbestic point at that particular point, and that isosbestic point is clearly indication that this even VO compound, even in this silent type ligand using pyridoxal as an side bond, it is giving almost similar result and converting into that. Now here, this is to give the reaction mechanism, we have used the homogeneous complex by studying the effective on vanadium NMR. Okay. Now, this is vanadium 4 compound. 15-1 NMR inactive. NMR inactive in general. So, in the beginning, what is recorded after keeping the sample in solution for say several hours, so that oxygen has entered into it and converted into vanadium 5. So the peaks here, two peaks are seen, and also possibility that it is oxidizing, as well as since this is done in DMSO, so partly DMSO can coordinate to the metal center. So partly DMSO coordinated and the pure metal. So two peaks are seen there. When you further add H2O2, the peaks are better and better. And then also another peak you can see that is going due to the formation of the peroxo compound. Okay. Then move further, more peroxide species found, and then you add, what is that, uh, where is there's one peak that is where it is added the substrate reacts with, okay, the top peak you will find that is after 30 equivalent, one peak is last one you will that methyl penyl sulfite. Okay, so immediately that peak due to peroxo has gone. That gives a clear indication that the peroxo is transferring oxygen to this one. So alternate way you can find out to give the reaction mechanism. This is theoretically predicted through theory DFT calculation, where it is possibility of the 51 vanadium NMR. You can see that, and it is predicted that the same way monoxo is going to dioxo, vanadium 4 to vanadium 5, then 5 is going to the peroxo, and then peroxo, when you add methyl phenyl sulfide, like when you have excess peroxo, it can go to the metal free ligand free metal complex, and can go back. When you add sulfide, it can go to the peroxo, and if not excess of hydrogen peroxide, then it can convert back to the dioxo. So mechanism can be given. Okay, EPR for vanadium 4, that is helpful. So we have EPR for the compound, have H2O2, then after having added the methyl phenyl sulfide, or you see that the EPR is coming back. So if compound is not exposed to oxygen, when it remains in +4 oxidation state, and if you do the S2O2 calculated amount and have added hydrogen, of course, the methyl phenyl sulfide, you should be able to add the conversion going back to vanadium 4 compound, not vanadium 5. Only thing is you have to have a small amount of H2O2 added, then you should be able to see that such kind of changes. Okay. So this is one also, that is manganese compound. Quickly I'll show that. Okay. And this reaction we have done that. And remember that in previous chemistry I told you about the oxidative bromination of Zeolite-Y. Oxidative bromination of Zeolite in KBr. So here with the manganese compound, manganese analogs can work very well for haloperoxidase model. Manganese, molybdenum, tungsten, these are the metal ions which works very well or go along with the haloperoxidase activity. So we have tried with the bromination of the styrene. And in this case, we observed the formation of three products. One dibromo, one of monobromo with hydroxyl group, the other is like diol. Okay. And if you look at that, first the optimization, obtain the optimized reaction condition and do the bromination. Fantastic reaction. Haloperoxidase model reaction can be tried with this one and giving a good result. Okay. And again, to give the reaction mechanism or to propose the reaction mechanism, this is one of the way to see that. Do the add the H2O2, then add the KBr, and at the substrate you will see the changes. Okay, that is the best way to go for any catalytic reaction procedure. Okay, so far what I told you, that these catalysts are so good, but earlier due to restriction, or you can say that with the non-availability of a lot of instruments at our place, we restricted with certain reactions, but we observed definitely some good results. But what I also observed in the literature during the 1990s up to 2010, people were inclined towards the discovery of the heterogeneous catalyst through the zeolites. After that, not much chemistry you will find in the literature. But suddenly, last few years, particularly I'm talking about metal complex in zeolites, chemistry again is started. Okay. And this paper, just see in organic chemistry, is 2019. This paper by Wits Pilani. Wonderful paper. When you go through that, they have prepared the palladium compound. I was discussing morning palladium compound. Okay. So they have prepared palladium compound. Look at the ligand what they have used. Almost same ligand what we have used earlier. Okay. But what they have done, instead of orthophilindiamine, they have taken metaphilindiamine 1,3 and palladium compound. They have studied the what is called the effect of the substituents in the cavity, and then what the chemistry can be done, Heck coupling reaction. Okay, I'll show you. So see now better instrument, and look at the crystallinity of these materials. Perfect. Other one where you have a metal complex on the surface, also uh, on the surface metal ions here, perfect neat crystallinity can be seen. And then, well, this is facilities available, VET, sorption, you can see that, okay, everything. Now, because facilities are available, now XPS can be applied in this case also, because you have metal center. So, all due to nitrogen, due to C development, everything you can see here, and metal content also you can see that. And then the reaction. Heck coupling reaction, well known reaction for the organic chemist when they start with. Or the palladium chemistry, when you have Heck coupling reaction, is most popular reaction. If you have a palladium catalyst, 90% papers you will see that Heck coupling reaction, different substrates, that's all. Okay, so they have done Heck coupling reaction, and this, look at this recyclability, 5 times they have done it, and perfect. So, good paper, good study, good journal, right? Another one, same group, because now facilities are available. All right, Heck coupling reaction, palladium Heck coupling reaction. You know, if I wish, I could do now chemistry start again. The Zeolite encapsulated, I have lot of ideas. I can do that. I've shown in the last few transparencies in my polymer supported materials where we have done multi-component reaction. It is going to work because all substrate can enter into the cavity, interact with the metal center, and still can pass through that, because those molecules are not bigger molecules, can come out of the cavity, okay, easily. Here, one of the important reaction related to pollution, carbon dioxide capturing. This project is going at very large scale. Now papers are coming, lot of papers are coming on this one. Okay, theoretical study, sir, theoretical study is also coming. Okay, yeah, that's why I put theoretical study. Also the experimental, because CO2 capture, cycloaddition to the styrene epoxide, etc. All epoxides, these days are coming like a hot topic. Another one journal is coming up, CO2, Journal of CO2, Journal of CO2. Separate journal is coming devoted to this chemistry, and the Zeolite and encapsulated complexes are working very good. They have driven it this mechanism. Yesterday only I reviewed one paper called the New Journal of Chemistry. It's coming only carbon dioxide cycloaddition reactions. It's coming up very good. Same group, see, inorganic chemistry frontier. What is this? Again, the same group, and now here they have replaced palladium with the nickel. Same, right? Nickel, palladium, platinum. What is chemistry? Now I don't need to say that. Okay, Heck coupling reaction. Just I brought it to just show you that now interest is growing in this chemistry. Okay, and this, what is called that? Another group, this group. If you look at there, we have prepared the same compound 20 years back. 2004-5, they have used the same complex, same metal ions, same ligand, and published paper here. And what is oxidation they have done? Same reaction they have done. It's just like they have quoted our paper also, but repeated the whole thing. Just copy paste kiya. Oops. Okay. So reaction is coming up. Benzyl alcohol. Just to show you, the molecular catalysis paper came. All right. And this paper came just ACH Omega only last year. So what you see that now the interest in this chemistry is increasing these days. That's what I brought these things here. Okay. So now question comes here. Whether zeolite encapsulated complexes serves as a sustainable catalyst? Answer is yes, of course, yes. I wish I could do this chemistry, I could start it. But now my days are over, your days are coming up. Okay? Because you are, if I talk about myself, this is third generation. Okay? Third generation was always better than the first one, and also better than the second one. Okay? You can think better. Because these catalysts may meet the industrial demand of recyclability for continuous operation. Definitely is going to work better. And they have done 5 cycles. People have done sometimes 10 cycles, 15 cycles, where facilities are available. We are limited to, students are limited to PhD degree. Okay, IIP people, Dehradun, they do 30, 40 cycles to show that because they have to sell the product in the market. So they do that much cycles and so that catalyst is working very well. Okay. Part of the people earlier, II people, they have done zeolites. They have stopped it because this government order what they have to do that. Okay. So, but the field need to be explored because not many reactions are known in this area. You can extend it because you have heard the lecture. Now you can go through the literature. Characterization is not very difficult these days. Very, I mean, set characterizations are there. All facilities are available. Now people can do it. And all chemistry what can be done with the regular homogeneous catalyst, all chemistry can be done with this heterogeneous catalyst. Okay. I dropped this idea because limited facilities were there. And then when we picked up the polymer supported students, see students they want degree faster. They wants to stay here longer period of time and want a degree without doing something. Fellowship is very important. All right. So I think thank you so much. I have come to an end. Okay. The same slide repeating. Thank you so much. Any question? You can ask how to start. How to start geolite chemistry? I can answer it. How to start vanadium chemistry? I can also answer. Yes, of course. Yes.
You have proved that professor cannot be retired.
Yes.
In overall lecture I have said. Some queries I have. In several conversion, you have used H2O2. Why not other peroxide, organic peroxide like
I
R2O?
have used one place TBSP. I have shown you TBSP. TBSP, tertiary butyl hydroperoxide. See, you can also use oxygen. You can also use oxygen. Oxygen is a slow process because if you use atmospheric, this is going to take a long time. And the other problem is that, see, people have done that. What you're talking about, people have done this. The other way where they have a continuous flow reactor with oxygen, you can be entered into like you have a like a block reactor, okay, and in the pipe you have put the catalyst, all right, and then you put the oxidant, you put the other materials going into reacting on the surface and giving the product. It is there. There. See, working in the lab, you have certain restrictions. We cannot use oxygen as a source. The reason is because control. Maximum you can use balloon. Okay. We tried. Once I thought, let's have a, pressure reactor. Pressure reactor where you have a what is called that reaction flask, stainless steel flask. You have all you can autoclave. The other way to say that the pressure reactor that is called autoclave where you can use continuous flow process. Autoclave you can increase the pressure. You can do the reaction. Okay, with the help of NCL in the beginning I tried it, but how long you can have help from others? You have to be independent, right? All the time when you grow, when you have comes to the promotion, people appreciate in the beginning. When it comes to the promotion, you are taking help from NCL. What is your contribution? They are contributing more, you are contributing less. I also ask the same question because I'll be sitting other side of the table, right? The same thing it comes. No, this is reality. This is reality of the world. Hey, भाई recording बंद कर दो हो गया. Okay, this is a reality of the world. Okay, so you